Potential due to an electric dipole. So electric dipole consists of two charges q and minus q separated by a small distance 2a. Its total charge is 0. It is characterized by the dipole moment vector p, whose magnitude is q into 2a, and which points in the direction of minus q to q. We also said that the electric field of a dipole at any point with position vector r depends not just on the magnitude r but also on the angle between r and p. So between this r vector and p, so further the field falls off at large distance, not as 1 by r square typically of field single charge but as 1 by r cube. We now determine the electric potential due to a dipole and contrast it with the potential due to a single charge. So as before, we take the origin at the center of the dipole. Now we know that the electric field obeys the superposition principle since potential is related to the work done by the field. Electrostatic potential also follows the superposition principle. Thus, the potential due to the dipole is the sum of the potential due to the charges. So, potential due to the charges, that is equal to q upon r1, q upon r2. So, now our geometry is this r1 square is equal to r1 square is equal to r square plus a square minus 2a r cos of r1 square plus a minus 2a r cos of theta. R2 square is equal to r plus a square plus twice a r cos of theta. So we take r much greater than a, r very greater than a, and retain terms only up to the first order in a by r. So r1 square is equal to r, that is a minus 1 minus 2a cos of theta upon plus a square upon r square. So equivalent to this, similarly r2 square is equal to this. So using the binomial theorem and retaining terms up to the first order a by r. So that is equal to 1 by this and this is equal to 1 by this. So V is equal to Q. Now putting the value of 1 by R1 and 1 by 2, so we get the, and P is equal to 2 QA, we get the V is equal to P cos theta 4 by R square, 4 by epsilon naught R square. So P cos of theta P into R. So the R dash is the unit vector along the position vector OP. The electric potential of a dipole is then given by this. So equation 2.1 is as indicated approximately true only for distances large compared to size of the dipole. So that higher order terms in terms of A by R is negligible. For a point D, find dipole B at the origin. However, V is equal to plus minus 1 by 4 pi epsilon naught P by R square. So positive sign for theta is equal to 0, negative sign theta is equal to pi. Potential in the equatorial plane theta is equal to pi by 2 is 0. The important contrasting features of electric potential of a dipole from the due to a single charge are clear. Potential due to dipole depends not just on r but also on the angle between position vector r and the dipole moment vector p. It is however axially symmetrical about p that if you rotate the position vector r and p about and p keeping theta fill the point charges points corresponding on to p on the cone so generated will have the same potential as p. Electric dipole potential falls off as a large distance one will not as 1 by r. The characteristic of potential due to a single charge. So